next thing that we can talk about is force. Now, force is basically the thing that you experience when someone pushes you. So, let's say there's this box here. If you push it, then you will experience a force and you will move in this direction. If instead this person was pulling it, again, you experience a force. The box will experience a force and it will move in this direction. So you can see that the force can actually change the direction that an object is going to go. Or if we were doing if it were a car, so well, a car would be on wheels and it was perhaps moving in 1 meter per second. If you imagined a another car or a tow truck, if you will, it's pulling it. Then and this one is driving at 3 meters per second. This will pull this car. So pulling this car makes this car move faster, as you would imagine. So as you can see here, force affects the direction and the speed of an object, of any object. Any and all objects that is in motion have to have experienced force in some kind. An object would not start moving by itself. A force must be applied upon it for it to start to have a motion. Any object in reality that has motion has experienced some type of force. The unit for force is Newton, named after Isaac Newton. Uh, so its unit is a capital N. You can measure force with something like a spring balance. Now I can't draw a spring balance, but it's basically a spring connected with a hook. So when you apply a force to it, the spring would be expanded. And judging from this expansion of the force of the spring, you can determine the force. So, to better understand and better illustrate force and how it interacts with everyday objects, you need to know how to understand and also draw your own free body diagrams. So what does free body diagram means? It's basically a simplified representation of an object and the force that is applied upon it. Emphasis that it's only on one object. If it's connected to anything, it won't be included, or it would be just summed up into one object. And as it is a simplified diagram, any and all object would be just resulted in a square. So let's say there's a gigantic ball on the ground, and someone were to attach a rope on it and pull it. So if that person were to pull it, there's one object here and two objects here. So if you were to draw a free body diagram of the ball, of the force that acts upon the ball, you would draw first a square, which is representation of the ball, and then a force in the direction which is applied. Now, to represent this ball on the free body diagram, you will first have to draw a square, which is this is the ball. And of course, you know that there is actually a person pulling here. So but you will not include this person inside your free body diagram because your free body diagram only has one object. So if it only illustrates the object that is where the force is acted upon. So let's say, so in this instance, it will be having a force acted upon here. Note that the tail of your force, which is always represented by an arrow, which is the direction of force, and also the size of the force. You can see that in this here, the arrow is longer. So the longer arrow applies stronger force. So it's actually pulling harder. And this is a shorter arrow, it's pulling shorter. It's weaker. But if that arrow is in this direction, it's like this, then it's in on the other direction. As you can see here, that the ball is being having a force acted upon it. So the end of your force must be at the point where the force is being applied on. So if I were to push it here, the force would be here. And though, in another case, if your object was actually like this, so there's a person pulling at it, the force it is acting on another object is not included in your free body diagram, but still, it will still experience a force that you're pulling upon it. But at the same time, there is also a force called friction, which opposes the direction in which the object is moving. This friction is basically an opposing force. Its direction is always opposite of its motion. So if there were a box moving in this direction, the friction must be of this direction. This friction is caused by the contact between an object and a surface. It is dependent on the roughness of the object and the surface, the contact surface. You could basically imagine on a very micro scale that any surface is not smooth. So you probably have some cracks like this. And your box may look smooth, but it actually also looks like this. So when they're in contact, every object it may be it will have a it will be trapped upon each other. So it actually makes a opposing force that pulls the the object in the opposite direction. So in this case, the ball is rolling down, but it also has a contact surface between the ball and the slope. So it will have a friction on this direction. So you can draw it on your free body diagram like this. There is a lot of types of force that is similar to friction. Something that is called water resistance. If anyone has actually been swimming before, you would know that when you're swimming, you always feel that there's a drag force. There's a force that's pulling you back when you're swimming forward. That is what you call water resistance, which is the force that the water is applying on you when you're moving in it. So water actually applies a force to you. Or if you're a bird or a plane or an object that just, let's say a ball that is flying in the air, it also will experience something called air resistance. Now, what is that? From your lessons on particle theory, you should know that air is made up of gas and there's molecules. Each molecule, when you move across it, you will hit them. So when the molecule hit it, they will have a force, a collision force, which pushes the object backwards. So there's a total force that is pulling it backward as the object is moving forward. And this is called air resistance. Now, the opposing force that we have just mentioned are, if you remember, have to be dependent on there to be a contact surface between the object and the surface. So there has to be contact Or if you're pulling it with a string or a rope, you have to be connected to the block. There's a connection here. Or if you're pushing it or pulling it, again, you are applying force on the object. So in all these cases, all these forces are contact forces, where you have to apply direct contact on the object. But also at the same time, there are non-contact forces. As you have demonstrated before, as I have cut out, if you remember just now, the unit for force is actually Newton. So what is Newton most famous for? Is for the apple that fell on his head. If you were listening, you would remember that that no object would move on its own without a force applying on it. So for a apple to fall, it has to have a force that is pulling it downwards. But then the apple is on a tree. So why would it fall down? That would be gravity. So that gravity doesn't actually touch the apple. So you can see that the apple is experiencing what is called a non-contact force. Any and all objects experiences gravity, and it is actually a force of attraction. So this object could be attracted to this object through gravity, and this could be attracted to this, and they are not in contact. So they are experiencing a non-contact force. Now, there are actually a lot of applications for the opposing force that I've mentioned just now. For example, friction is something that is essential for our daily life. Let's say if you are walking, friction is what allows you to walk. Your feet steps on the ground as you try to move forward. As you move your leg backwards, which is in your motion of walking, the contact surface between your feet and the ground provides a friction force forwards, which allows you to move forward. Or if you're trying to use your hand to hold something, sorry for a bad hand drawing, the contact surface between the hand and the object actually experience a friction force upwards, which prevents the object from sliding out of your hand. So if you were able to ever hold anything or touch anything or move anything, that is because of friction. But these opposing forces could also be restrictive in a daily life. For example, if you're driving a car and you want to drive it as fast as possible, but as there is a air resistance that is dragging your car back, you won't be able to move as fast. So a solution would be driving a more streamlined car so that the air will actually not hit directly on your car surface, and therefore the air resistance will be smaller. Or if you have a parachute, you would actually want to increase your air resistance. So you will have to make a larger parachute so that there's more air surface contact surface between the air and the parachute, so that your air resistance would be larger. There are many ways to minimize or maximize these restrictive force. For friction, you could install something called ball bearings, which is basically a lot of balls put in a track so as to reduce friction, as a rolling motion is actually experiences less friction than the sliding motion. So to maximize this reduced friction, you put them in a ball bearing, and when you move, all these balls will roll instead of slide, reducing friction. So going back to the object we talked about before, well now it's a box. Before it was a ball, right? So let's draw a free body diagram for this. So there's a person actually pulling here. So what are the forces? What is the free body diagram of this box? So first you have to draw the box. Only the object. No need to draw the surface, the rope, or the person. Only the box. So there is a friction force. No, there's a force applied by this person. So applies to this direction. But as you have a force applying in this direction, its motion will be in towards this side. So as it has contact between the box and the surface, it would experience a friction in this direction. Then we can think about the idea of gravity. Now again, every object experiences gravity as the Earth has a very large mass and everything wants to go to the center of Earth. So it would experience a gravity, which is what we call weight. It will experience a weight, which is go directly downwards. But as you can see, the box is actually on the surface of the land. So the land actually applies a force back up. So this is the free body diagram of the box. So this is what we call the force. This is the friction, the weight, and the normal force. Now the normal force, what is the normal force? The normal force is the reaction force where if you put an object on a table, the table will apply a force on the object to keep it from falling through or moving at all in the vertical direction. So why any object can be placed on any other surfaces is because the surface would provide a normal force. We remember, as we said before, that every object experiencing a force must be in motion. Then why you can put something on the table where it experiences a normal force but it doesn't move? So if you put something on the table, what are the forces that it is experiencing? So, like we said, the normal force, but also its weight is pulling it down. So imagine having a tug of war. If two person is pulling in two directions, the objects in between won't be moving as both sides cancels out. So this is the same here. As the object experiences a force upwards, it will like to move upwards, but also experience the same force that is of the same size, but in the completely opposite direction. So its motion is cancelled out, doesn't move. So when an object has balanced force, it will experience no force at all. So let's say two person pulls this direction, then this would have no motion. It will not be moving. Now, if you remember from before, I've said that an object on Earth would experience gravity that pulls it downwards. As a matter of fact, any object with a mass will experience a gravity, a force of attraction. This is what gravity is. It's a force of attraction, a non-contact force of attraction between two masses. So, a force, but important thing to distinguish here is that gravity is in fact not a force. It is an acceleration, which is basically the rate of change of speed, or in this case, more accurately, velocity. The actual force that any object experiences downwards is called weight. Now, what is weight? Weight is, again, of course, a force. This is the force that pulls objects downwards, not gravity. There's a difference here. Gravity causes weight, and causes there to be a force, but is not the force that drags things down. In fact, here's the equation. Weight equals mass times gravity. The weight, which is the force that an object experiences downwards, is supplied by the gravity, but is not gravity. And in fact, the weight is dependent on the mass of an object. So if your object is much bigger or compared to a smaller object, the weight would actually be much larger, despite the gravity is same. Gravity is a acceleration provided by the Earth. It makes every object in the vicinity of Earth have a acceleration towards the Earth's core. Acceleration, again, is rates of change, which is meant by meter per second squared, where rate of change is the change of speed over time, which is already meter per second over a second, so it's meter second square. The gravity on different planets is not the same. The gravity of different mass is not the same. But the weight is in fact the measurement of gravity. Now, I mentioned that weight is equals to mg. But you may be wondering, what is this? It's mass. But how is this different from weight? Well, the weight, as you can see here, is dependent on gravity. So if you were on Earth and on the moon, your weight would be different. Why? Because the gravity itself is different. So as gravity decreases, the weight also decreases. But you, as you're the same person, has the same mass. So what is the measure of mass? It's a measure of the amount of matter in a substance or in an object. So a thing with maybe like only 9 particles and one with 4 have different amounts of matter. So this has a lower mass, and this has a higher mass. Yet, if this one is placed on the moon and this one on the Earth, this one could have a higher weight, or this one has a lower weight. So this is the relationship between weight and mass. So as we said, weight equals to mg. Now weight is a force, and g is acceleration. This actually is derived from the actual definition of force. So what is force? It's actually F equals to ma. Again, A is acceleration, and force. What is force? So remember this. When an object has a higher mass, the force acting upon it has to be higher so as to achieve the same acceleration. And if the object is experiencing a higher acceleration with the same mass, it means that it is also experiencing a higher force. While if the object is experiencing a slower acceleration, then with the same mass, the force is smaller. Or if the acceleration is the same, but the mass is smaller, then the force applied is also smaller. So that's the relationship between force, mass, and acceleration. Now, hopefully, this video has been helpful to you, and thank you very much for watching. Don't forget to like and subscribe